Log on, tune in, find out. Another good idea from Cambridge.
Got some client who needs some new cryptographic system. It's going to be a solution to some big problem, and so he sits down with the project manager of the solution provider, and they talk about security goals and threats and all the kind of things which we know we'd like to do in a really in-depth threat analysis for the solution. And then the project manager goes to talk to his engineer, and they spend a good time talking about exactly what these threat scenarios are and exactly what the goals are, and then the engineer comes up with his formalized security notion of exactly what kind of scenario his crypto algorithm is going to have to resist in order to be an adequate solution for the problem. And then he goes to the literature and consults all the relevant publications, comes up with a nice scheme, and and makes sure that it complies with the system. It's got a nice proof, and then we have a nice secure system, right? Okay. So obviously this is dreamland. Nothing like this has ever happened in any project that I've been involved in. What I've seen happen, usually before I get involved, is something a bit more like this. So without any consultation with the client whatsoever, a couple of engineers get around a whiteboard and come up with various things that they've never implemented before and thought might be fun to implement, and plan some fun crypto stuff. Then they consult the literature. In order to find out how to do that, and then a short amount of time later, the literature is augmented by a series of papers showing how to attack the system, how they shouldn't have used the same nonsense all the way through, and they shouldn't have used these old mechanisms without authentication and what have you. Okay, but fortunately, I think that's happening a bit less now. So more often, as we've been talking about, the real scenario is something a bit more like this. So the project manager sits down with the client, and the client says, well, I don't care what you're going to do, but I've got this huge warehouse full of PKCS11 compatible devices, and I'm going to use those because they're very expensive and I don't want to buy a lot more. Okay? So the project manager goes to his engineer and says, well, I don't care what you come up with, but it has to be something which uses the PKCS11 API because that's what my client wants to use. Okay? And so what this talk about is about what happens next. Okay? So how do we actually end up with a secure system? So, and I picked the example of PKCS11 because it's essentially the most popular standard in use for the interfaces for cryptographic devices. So just in case you're not familiar with these PKCS things, so this was a series of standards that are essentially edited by the RSA company that now belongs to EMC. So they invite contributions from outside, but they decide what ends up in there. And so you've probably all looked at some point at RSA PKCS number 1 because that defines how to use the RSA encryption algorithm, how to do the padding and all this kind of stuff. And there's a whole bunch of other ones which describe things like certificate formats and how to do password-based encryption and all these things. And number 11 defines this interface, which is called CryptoKey, which is a sort of abbreviation for cryptographic token interface. And it's used everywhere in industry, from little things like authentication tokens. So this is an authentication token, a little USB device with a little crypto processor and a little bit of memory inside, to smart cards that you have in your pocket for paying with and running EMV and all these kind of things. Okay, those ones don't have a PKCS11 interface probably, but other ones do. And they're used in HSMs, these big expensive devices that we've already been talking about several times today. So the first version of PKCS11, and this is kind of important because it's quite old, right? So the first version of the standard came out in 1995, so that's prior to things like the Bleichen-Bakker attack on RSA PKCS1 version 1.5 padding and things like that. And the current version is not all that up to date, so the current version dates from 2004. There is a sort of public consultation draft for version 2.3 that's around at the moment, but the current version in use is version 2.2. And in fact, if you buy an HSM now, there's a very good chance it doesn't even support version 2.2. It's quite likely to support an older version like 2.1, something like that. One of the reasons for this is that building that kind of hardware, like those HSMs, has a very long lead time. It costs a lot of money for a company to design a new HSM, and so then they try and sell them for a very long period afterwards, right, to recoup the design costs. So if the new version of the standard comes out and demands algorithms which are not in the box, then tough, you don't get the new version of the standard on your box. Okay, so how does PKCS11 work on a very high level? So roughly speaking, you've got your host machine on the left-hand side, and in the worst case, something bad might happen here, like a virus or a malware or just a malicious user who's trying to get hold of the keys. And on the right-hand side, you've got your trusted device, so your HSM or your smart card or what have you. So this is sort of tamper-resistant memory in some sense here. and this is sort of here be dragons, bad things happen here. So the way it's going to work, very basically, is like this. So we're going to store some keys in the trusted memory on the right-hand side. So here's a key K1, and each of these keys is going to have a handle, okay? So a handle is just a pointer to a key, or a name for a key, you can think of it as, depending on your favorite abstraction. It's just telling you where in the secure memory this key1 is stored. And along with each key, we're going to store some metadata, okay, which describes the usage rules for the key, perhaps its history, when it was created, its validity date, and all this kind of thing, and what its usage rules are, okay? And in the PKCS11 language, this metadata is called the attributes of a key, all right? So that's very simple. So yeah, just to make it very clear, if you know the value of n1, so I know the value of the handle, that shouldn't in general tell me anything about the cryptographic value of the key, okay? It's just something that tells me how to refer to that key when I'm making an API call. So let's try generating some keys with PKCS11. So if I want to do that, I have to give to the interface something called a key template. So that's a partial specification of the metadata for the key, okay? So it might tell the device some of the things I need to know about the key, and then the device might add some default values, this kind of thing. And I'm going to use templates in other parts of the API, okay? Every time I create or change the attributes of a key, or I want to look for a key. So the command, which in the interface is called C generate key, so all the commands start C underscore just for crypto key. So I'm going to write it in this very high-level sort of schematic way. So I'm going to have some inputs on the left-hand side. I'm going to have an arrow, and above the arrow I might have some things which happen, some things which are generated inside the device. And on the right-hand side I'm going to have the output, okay? So what this saying is you give me a partial template. I'm going to generate you a new handle and a new key. And I'm going to give you back an association which binds this handle n to this key k, and I'm going to set the metadata for this key k to some other template t, okay? So this is all very informal, but the reason I've written this t in one typeface and this in another is because the actual template that your key gets may not be the template that you asked for, okay? It's quite typical inside these devices that you ask for something and the device goes ahead and makes something a little bit different. Okay, so that's how we generate keys. But that's not the end of the story for the attributes on these keys. I can later on decide that I'd like to change the attributes on a key. So I would do that by using the command C set attribute value. I would give the template for the key that I would like to change, so that's the new values I would like to give to the attributes. I give my handle, which is pointing to a key, and the device will return me the same handle, but now with an updated template T. And again, the relationship between the template I asked for and the template I actually get is sort of underspecified and relies on particular implementations of the standard. And my device might refuse to do this as well, okay? So I can specify anything in this template that I'd like to be changed, but I might get some error codes back from the box, which might say something like template inconsistent, or if I'm trying to overwrite an attribute which you can only write once, I might get a return code saying read only, okay? Just give you an idea of how these things work. Now I have two really exciting commands which are fundamental to the way that PKCS11 does key management. So these are used for secure transport of keys between devices, or they could be used for backing up a whole load of keys onto insecure storage that I'm going to use in a single device. So they're called wrap and unwrap. So Christian's already mentioned key wrapping today. So wrapping is very simple. I have two keys on my device, so they both have pointers. One of them has the attribute for wrap set to true, and the other one has the attribute extractable set to true, okay? And the result is that I get the extractable key, which is y2, the one pointed to by x2, encrypted under the wrapping key, which was the one pointed to by x1, okay? So that's great. So then I've got now an encrypted blob, and I can send it to another device. And when it arrives at the other device, I need to have a copy of the decryption key. So here it's y2. That one needs to have the unwrap permission x2. I give the template that I would like to give to the new key that I'm creating. My device will generate a new handle, a new pointer, and then it's going to give me back the association between this new pointer n1 and the key that was inside the blob y1. And notice that according to the standard, the new template, whatever it is, has to have at least the attribute extractable set to true. So why is that? The idea is that PKCS11 is trying to remember that this key came from the outside world, okay? So this is a key that came in from somewhere else. It was unwrapped, so it's always got to have extractable set to true. Okay, so that gives you a flavor of that. So here's a little example in a picture. So I've got a key K1. It's got the attribute X. That means extractable because I'm going to use E to mean encrypt. And this one, K2, has got the attribute W, which means it can be used for wrapping. And this should mean that I should be able to see outside the box the blob key 1 encrypted under the key K2. Okay. And then I have the commands you might expect for using these keys. So really, these keys get used in a three-part command that does an encrypt init, then it does an encrypt update, and then finally it does an encrypt finalize. Okay, so this is for going through a big block stream, something like that. But in my abstract model, I'm just going to consider these as atomic commands. So I'm going to have some pointer x1 that points to a key y1, and I've got some blob y2 I'd like to encrypt. And if I have the encrypt permission on that key, then the box will give me back y2 encrypted under y1. And similarly, if I have some blob encrypted under y1, which has the decrypt permission, then I can get back that blob y2. Okay, so we've seen a few basic commands. So there are a whole bunch more for things like max and signing and verification and all this stuff. But let's see what we've got so far. So what does it mean now to talk about the security of a device that supports this interface? Well, it's not entirely clear, but there is a little discussion in the standard. So the standard is just under 400 pages long, and the security discussion is just over 1.5 pages. And so in our ideal crypto world, we might like that to give a lot of formal specifications of exactly what properties are for a particular key given a particular set of attributes and this kind of thing. But of course, that isn't really what's there. What there really is just a few paragraphs of kind of natural chat in the sort of English that you only get when you design something by committee. So here's what it says. So access to private objects on the token and possibly to cryptographic functions and or certificates on the token as well requires a PIN. Okay, so what that's saying is if I want to talk to one of these cryptographic devices with PKCS11, the first thing I have to do is open a session with that device. And to open a session, I need to supply the user PIN. Okay, so this is the sort of first line of protection on all these devices. It's worth keeping in mind that the PIN might be typed by a user on potentially on an insecure machine, or it might be the password might be written to a file on the drive somewhere. So this is not the only bit of security that you get. So here we have another nice sentence. So additional protection can be given to private keys and secret keys by marking them as sensitive or unextractable. So when they write marking a key as sensitive, what that means is you have an attribute sensitive, and if you set that to true on a key, that's what it means to mark a key as sensitive. Okay, and marking a key as unextractable is the same, except you set the extractable attribute to false. All right. Okay, so far so good. Sensitive keys cannot be revealed in plain text off the token, and unextractable keys cannot be revealed off the token even when encrypted. Okay, so there you have a security policy now. That's fairly clear, right? That tells us how these attributes should relate to the policy for the keys. Then there's a little bit of chat that says, rogue applications and devices may also change the commands sent to the cryptographic device to obtain services other than what the application requested. But they cannot compromise keys marked sensitive, since a key that is sensitive will always remain sensitive. Similarly, a key that is unextractable cannot be modified to be extractable. So what that means concretely in the standard is that I showed you that set attribute command, right? And I said you can give a template and say, I'd like to change the template of that key to this new template. But if you have a key that has its sensitive attribute set to true, and you supply a template where the sensitive attribute is set to false, the device is supposed to refuse, right? It's supposed to say attribute read only. You already set that thing to true, you can't now set it to false. So it's a one-time decision. You marked your key as sensitive, and now that's it, it's secure. And similarly with extractable, once extractable is false, you can't supply a template with it extractable set to true and then call set attribute and get it set to extractable. Okay, that's how it works out. Okay, so let's see that in our little picture. So here's our two keys. So key 1 has the attribute extractable and sensitive, and key K2 has the attribute wrap. So it should be the case, if we follow that security discussion, that the only thing we can see outside the device should be this key K1 encrypted under K2. Okay, so we can't see K1 in the clear because key 1 is sensitive. So if we demand to see the value of K1, and there's a command for doing that, the command will say, this key is sensitive, you can't see the value. Okay, it's going to give an error message and refuse to do it. We can't see K2 because key 2 is not extractable. So this is a bit more ambiguous from that discussion, right? So remember what it said at the bottom here. A key that is, here we go. Unextractable keys cannot be revealed off the token even when encrypted, okay? So for me that implies that they certainly shouldn't be able to view them in the clear. But notice that that's not explicitly stated in the standard. So that will be relevant later on. So we can't see K2 in the clear because even though it's not marked as sensitive, it isn't marked as extractable either. So that puts it at the top of the hierarchy of keys we can't see. We can't wrap key 2 with key 1 because we don't have the wrap permission for key 1. So the only thing we should be able to see is this blob key 1, K2. Okay? But then suppose we have permission to do decryption using the key K2. Okay? So what that means is I can supply an arbitrary ciphertext to the device and ask it to decrypt it using the key K2. So then I can just apply this blob, ask it to be decrypted, and suddenly I have the key K1 in the clear, right? So this was the key that I marked as being sensitive. And following my security policy, once I've marked a key as sensitive, it can never become non-sensitive, etc., etc., etc. But unfortunately now I've got the key in the clear. Okay, so this is bad, right? This is a very bad thing. This is exactly what the standard said I shouldn't be able to do. And in a paper at CHES in 2003, Johnny and Clulo published this attack and a whole bunch of other similar concerns about PKCS11. Okay, so we came to this problem in 2008, and we were interested in trying to find ways to show that a particular configuration of PKCS11 is secure. Okay, so it may not be that your system allows you to do this because the standard is quite underspecified and you might have implemented it in a particular way. So could we prove that a particular configuration of PKCS11 was secure? So what we found is it's actually very difficult. So you can, for example, prevent any key from having permission to do decrypt and wrap. That seems quite sensible, right? So your keys which are going to encipher other keys, you don't really want to use them to process data. So let's separate them into sort of separate use cases, okay, and that will be fine. But then what you end up with are longer attacks like this, okay? So this attack came out from formal work that was at CSF in 2008, where we actually built a formal model for the PKCS11 interface, and we were using a model checker to explore the combinations of commands to try and find these kinds of traces. So what's going on here? So now I've got a configuration where I'm not allowed to have decrypt and wrap set on the same key. But what's going to happen here is actually I'm going to make a copy of the key K2. First of all, I'm going to wrap it under K1. Then I'm going to unwrap it. Then I'm going to get a second handle, N3, which points to the same cryptographic value K2. Okay? So now I've got N3 pointing to K2, and I've got N2 pointing to K2. And on N2, I've got the permission to do wrapping. And on N3, I've got the permission to do decrypting. So essentially, I can go ahead and do the same attack over again, right? So then I still end up getting K1 out in the clear. So there we were in 2008. So we went to see some manufacturers at this point, and we said, look, we've got this really cool tool, a model checker. It's really fun. This formal method is really cool. Why don't we talk to you about your PKCS11 configurations so we can try and find out which ones are secure, this kind of thing. And the response was pretty disappointing. So essentially, people said to us, you know, don't worry your little heads about this. We have experts working on this stuff. Everybody knows that PKCS11 is completely open and insecure if you implement it in a naive way. But we have really smart programmers, so everything is fine. So at that point, we were faced with a choice either to drop the subject, move on and look at something else, or to try and make a tool that would actually execute these vulnerabilities on real devices to really scare these guys. So obviously, it's the second one that we did. So the tool is called Toucan, a tool for crypto key analysis. And it works roughly like this. So one thing we discovered very quickly when we started this project was that if you just take one of these attacks as it's written out like this and just try and execute it naively on a device, you normally get some error that doesn't really have anything to do with security, in the sense that just because you get this error doesn't mean that some variation of this attack won't work. What you would normally get was you would get something like, oh, you can't set wrap. Wrap is something you either set when you create a key or you don't. You can't set it later on, right? So then you have to go back and change the attack and make sure you set wrap at the time that you create the key. Or later on you would say, you can't do unwrapping under this key because this key has only the permission to unwrap and not the permission to wrap. So in order to prevent you from creating a key which is useless, some devices, for example, when you create a symmetric key, don't allow you to create one that's just for encryption and not for decryption. Because then you might encipher a load of stuff, then later on say, right, now I want to decrypt it. Oh, now I can't do it. And maybe I'm not allowed to set the decryption permission later on, right? So you come up against all these kind of things which are put there to try and perhaps help the programmer or make avoid some error cases, but they're not preventing the attack from happening, okay? So the idea of Toucan was that we were going to automatically find out what variation of the attack would be the best one to run on a particular device, okay? So the idea is that you plug in your device here, and then Toucan is going to send to the device a whole series of queries. It's not trying to make an attack, it's just trying to discover how this particular device has implemented the PKCS11 standard, okay? So it sends tons and tons of commands, it looks at the error codes it gets from each one, and it builds up a picture, in fact, a formal logical model in the same kind of language that I've been showing you, of exactly how this device has implemented PKCS11. So then it makes this model. Toucan sends the model to a model checker. So here we're using a model checker that was optimized for security protocol analysis, called SATMC. It could be pretty much any model checker. So it just happens that I worked on this project while I was working in Italy some time ago. So I knew which switches you have to tweak to get good performance and so on. But it could be any model checker here. The model checker churns away on the model. Eventually it comes up with a sequence of commands that it thinks will lead to an attack. Toucan turns that logical sequence back into real commands for the device, and it tries to send to the device to see if the attack will work. Okay? Very simple. So I'm going to do a demo of Toucan, but before I do that, I want to just comment a little bit about so all this stuff I've been talking about is at a very high level of abstraction, right? So I have these abstract symbols for encryption. I haven't said what algorithm I was using, what block cipher mode, or any of these kind of things. But we are interested in those subjects as well, of course. And I said PKCS11 was quite old, right? So it specifies a whole bunch of mechanisms which we would now consider insecure, things like single DES. And this can be a problem because in a naive implementation, you might allow, for example, a user to wrap a nice secure key, a 256-bit AES key, under a single DES key to export it, right? So in a sense, you get the security of the weakest point. And you get other problems as well. So, for example, there's no authenticated encryption supported in the current version of the standard. The new version is proposing some support for this. And for asymmetric crypto, so there is OAEP now, but in fact, it's PKCS1 version 1.5 is still in the standard, and it's used on almost all the devices. And most devices, it's exclusively that mode that's used, right? So a lot of old devices, you can't even get OAEP. And that poses a real problem, in particular for the unwrap command, okay? So remember what the unwrap command does. You give me a blob containing a key encrypted under some key that's already on the device, okay? And you're asking me to decrypt this blob and load that key into memory. And presumably this key you're going to load into memory is secret, otherwise you wouldn't have encrypted it to send it to me, all right? But now the unwrap command is going to be using an algorithm that supports, allows kind of padding attacks, right? So imagine that I can get hold of a padding oracle from the unwrap command. It's either going to unwrap the blob and say, okay, I accept that key, or it's going to unwrap the blob and say, oh, that blob has a padding error. Then that's giving me exactly the kind of padding oracle that I need to launch something like Bleikenbacker's attack, okay? And so Bleikenbacker's padding attack, of course, it's known as the million message attack, right? Because of the estimate of 2 to the 20 ciphertext that you need to decrypt a block. But recently we've been doing some experiments with optimizing the attack, because a million messages on a tiny little cryptographic device like this is going to take you an extremely long time, so it's not necessarily a very practical attack. But we've got some recent results which allow us to do the million message attack in just 15,000 messages median. So I was giving a talk about that here last Thursday. I won't talk about that today, but just to say when you see the results from Toucan, that'll explain why we have some very low numbers for the padding oracle attacks that you can make with this command. Okay. Oh yes, so I have to always mention that it's my wife who made the logos, so she made me promise to mention that when I show them. Okay. So I'm going to try and run Toucan on this. This is a Aladdin eToken Pro. So the only reason I'm using that is because it has a Linux device driver, and that makes it easier because I've got a Linux virtual machine. There isn't anything particularly unusual about the behavior of this device. Okay, right, so how does that look on the big screen? Not too bad. Yeah, okay, good. Right, so here's the pin. We're going to connect ourselves up to this PKCS11 device and see what it can do. We get a little bit of output. So notice that the manufacturer is now SafeNet and not Aladdin. That's because SafeNet took over Aladdin. And obviously the first thing they did was change the name in the device driver, even though they couldn't change it on the bit of plastic. So the first thing we're going to do is cheat a very little bit. So there are two kinds of keys in PKCS11 devices. There are token keys and session keys. So token keys are burnt or just written into non-volatile memory on the device so that next time you plug in the token you get the same keys. And there are session keys which are just written into RAM. Okay? And this particular device, being quite low powered, takes a long time to write keys into non-volatile memory. Okay? So that would mean the demo would take about 9 minutes, which is a bit long. We're probably all getting thirsty. So we're going to cheat, and we're going to use asymmetric session keys. It doesn't really make much difference for symmetric keys. I guess they're a lot shorter for the device. So if you want to see the demo with real token keys later, I'll be extremely happy to show it to you. Anyway, so let's launch the reverse engineering process. So what you're seeing on the side here is just the error codes we're getting. You see some failure messages. We're generating different kinds of key pairs with different attributes. We're testing the ways that we can wrap keys and unwrap keys. We're testing the attribute policy now, right? So we're trying to work out what restrictions there are on that set attribute command. We're sending different kind of templates, and we're looking for cases where we're not allowed to set an attribute from true to false, or we're not allowed to set it from false to true. Then we're looking for pairs of attributes that we can't set at the same time. So of course this reverse engineering process is necessarily incomplete, right? Very incomplete. So we're going to end up building a logical model that is an approximation of what's really happening on the device. And there's no way that we could send a finite sequence of queries and be certain about what was actually running on there. But the approximation that we get tends to be quite useful. So just to point out a couple of things from the summary that Toucan's giving us here. Notice that this is probably too small to read, so I'll just tell you what that says. This is telling us that for asymmetric keys, the attribute sensitive is sticky on. So sticky on is our way of describing attributes which, once they're true, you can't set to false. Okay? So that's absolutely correct. They've correctly implemented the standard in doing that. And here we have the attribute extractable is sticky off. Okay? So that's just the opposite. That means that once it's false, it can't be set to true. So these guys have obviously read the standard, so that's encouraging. Now we're going to make a model for the model checker. It's going to give us a default file name. So there's the model. So I'm not going to explain this in detail, but just to give you a sort of a quick look at it. So there's all these are set rewriting rules, technically speaking, and they have, let's just look at one of them. So what's going on here? Here's a rule for wrapping, and it's saying that if you know some handles pointing to a symmetric key and a private key, and you have the right kind of setting of the attributes on them, then you can end up knowing the encryption of the private key by the symmetric key. Okay. So now we're going to call the model checker. Now we have to be a little bit patient. Okay, right, so we've got an attack found. And so it's not easy to see what happened in this attack, right? Because the attack is coming back in the language of the model checker, these crazy rewrite rules, so it's very hard to read what happened. But if we actually try and execute it on the device, then we'll be able to see a bit more clearly. So let's try executing it. Okay, so what happened here? So the first thing we did was we generated a couple of keys. So we generated an asymmetric key pair where we have sensitive is false, extractable is true. These attributes, which are from PKCS version 2.2, are not used on this device. And we've got everything possible set to true so this is giving a composite of the attributes for the public part and the private part. So the public part has permission to encrypt, the private part has permission to decrypt, public part has permission to wrap, and the private part has permission to unwrap. And then we've got a sensitive key here, which has sensitive set to true. And so what we're seeing is just an instance of Clulow's attack, only here we happen to be using an asymmetric key pair. It just happened that the model checker found this one first. Okay, we don't really have control over how that works. So it's generated the encryption of, let's get this the right way around. So it's going to use the public part K2 to encrypt the symmetric key KS1, and that's going to result in a big RSA blob. And then it's going to use the private part of the key pair to decrypt that blob, and that's going to result in the sensitive symmetric key coming out in the key here. So that's just a hex code for the key. Okay, so that's sort of bad. So you might think, well, how can I reconfigure my token so this doesn't happen? So I'm just going to save the config, and I'm going to background that. So we have a sort of language for configurations for PKCS11 that Toucan outputs. So the first thing I'm going to do is I'm going to delete the templates, the set of allowable templates that were generated by Toucan for this model. That's because I want Toucan to recalculate that on the basis of a new configuration, which is what I'm going to do now. So we saw that it was a bad idea to allow keys to have both wrap and decrypt set on them, right? Warp. So we're going to ask Toucan to analyze a configuration where that's not allowed anymore. And I showed you the attack there for asymmetric keys, but clearly the same thing would work on symmetric keys. So to avoid wasting time, we're going to set that as well. Okay, so notice that Toucan's telling me that there were no set of templates found in the file, so it's going to calculate a new set. Let's just check that the app correctly passed the file, so it's noted that these two things should be conflicting now. So we're going to make a new file for the model checker. We're going to call the model checker again. And this is going to take a little bit longer this time because the most obvious attack isn't available. So I'm hoping, because sometimes we change the optimizations for the model checker and you get different attacks out that you weren't expecting. But I'm hoping that this attack is going to answer a question which Christian asked earlier during his talk, in fact. But we might have to wait a while. Going to the pub tonight? Oh yeah, okay, here we go. Great. So we found an attack. So again, it's hard to read, so let's try just executing it directly. Okay, good. So what happened here? So here we generated two symmetric keys. The first one has sensitive set to false and extractable set to true. The next one has sensitive set to true and extractable set to true. And so what I've done is I've asked to get the value of the non-sensitive key, okay? The value pointed to by N3, and that's giving me the non-sensitive value of this single des key. Then there's a bunch of redundant steps which have come in because of optimizations in the model checker, but which don't really need to be done. Then I've encrypted the sensitive key KS1 under the non-sensitive key KS2, okay? And then of course, because I know the value of KS2, because I asked for it here, I can do that decryption offline, and I can get the value of the sensitive key in the clear. So it's just the attack which you had at the bottom of your slide in the talk this morning.
I think that was from the old paper, right?
Well, actually, I don't think we had this one in our paper, did we? Or did we?
No, maybe from an earlier paper by Ross.
Okay. Yeah, most likely. Yeah. Okay, so this really does happen on. You were saying you weren't sure whether this was ever really implemented. Well, it is really implemented. So and we can keep iterating like that and try hammering down the configuration and restricting things until eventually we arrive at something that Toucan can't find an attack on. So then the question is, can we prove that that configuration is really secure? Well, the current state of the art with this is that if you have certain really locked down configurations, we can show with Toucan that they are secure for an unbounded number of fresh keys and handles that you generate using some abstractions which are similar to the abstractions used in the ProVerif tool of Bruno Blanchet. But for many configurations that we might suspect to be secure, we can't currently verify. And so that's sort of a current subject of our research. But let's get back to the talk. So here are some results from using Toucan on a bunch of devices manufactured by some relatively well-known manufacturers. So what have we got on this table? So here is just a basic summary of what kind of functionality we found on the device that Toucan found. And these are divided, by the way, just into form factors. So these are USB devices and these are smart cards. There's no quality difference between these. And on the right we have the attacks which were found. So in this column we show the first attack that Toucan found, and then you've just seen how by changing the configuration you can find new attacks, okay? So that's the extra ticks in this column. So the ticks here are saying that there was some variant of the wrap and decrypt attack. Either we were wrapping under a key that we knew the value of, or we were able to use wrap and decrypt on the same key, that kind of thing. It's often a different kind of variant. But now we come to the really sad part of the story, okay? So this is pretty cool. We're really happy with our model checker. It's very powerful. We can find all these different attacks. It's very, very cool. But a tick in this column means that if you ask the device just to read the value of the sensitive key, it just tells you the value of the key anyway. Okay, so after all that effort and all this kind of cool stuff, this was actually really depressing. And this is saying that you can directly read the value of an unextractable key, so one where the extractable is set to false. Yeah, and on the right-hand side there, that's saying that you can unset the... So remember I said that the attribute sensitive is supposed to be sticky on. Once it's on, you shouldn't be allowed to set it off. So this is saying that for these devices, you can set them on and off pretty much arbitrarily. Yeah, and notice that this Siemens device allows you to read unextractable keys, which are non-sensitive, right? So this is what I was saying about the spec just turned out to be not clear enough for the manufacturer to interpret. The fact that it didn't say explicitly that an unextractable key that's non-sensitive is even so should not be read meant that there was enough ambiguity that one manufacturer allows these to be read. Yeah, okay, what are other highlights of this? Oh yeah, so the RSA device. So these things are really expensive, right? So these cost about $300 a unit. Depends how many you buy and what your deal is. But clearly, yeah, so the amount of money that you pay for your PKCS11 device doesn't have much relationship to what kind of quality you get. And notice that probably the most depressing thing is that this column is saying, is it possible to wrap a sensitive key with this device? Okay, so some devices, like these ones, they don't allow you to wrap any of the keys. They can just be used to sort of manage a session key for something like SSL, or you can use them just to generate an asymmetric key pair, give out the public part, keep the private part, and sign some stuff, and that's all that the device does, okay? Which is nice, and then you don't seem to have any problems. But any device that allows you to wrap sensitive keys, so any device that has a tick in this column, also has at least one tick in the attacks column, right? So there isn't a device on the market that will allow you to wrap sensitive keys and also share them securely with other devices.
There's probably not a market for it.
Yeah, you'd think so. Yeah, I mean, clearly they sell a lot of these things, right? So anyway, so yeah, so this one, for example, is used in the Swiss ID card. So, I mean, there are a lot of those in circulation. Okay, so what happened so it's often interesting to publish a vulnerability report and see what the reaction of the manufacturer was. But in this case, we're going to publish a very similar vulnerability report to lots of different manufacturers. So that's quite nice. So it gives you quite a rare opportunity to do a sort of comparative study of the reaction of the different manufacturers. So RSA sort of swung into action. They registered the vulnerability with MITRE on this vulnerability list. And they issued their security advisory on the 6th of October 2010. So that date's significant because it was the date that I was giving the presentation at CCS of this set of slides, right? So at the same time I was giving it, they were telling their customers. But their solution is not entirely satisfactory. So what they're going to do is essentially block the problems with reading sensitive keys at the level of the driver, at the level of the device driver that you download and install on your host machine before you speak to the USB device, okay? So if you don't update, or if you're an attacker and you just decide to use last year's device driver, you can still go ahead and read them. Presumably this is because they have somewhere a warehouse containing 100 million of these keys that they really need to sell to make their money, and they don't have any way to update the firmware on them. You can read the responses from Aladdin and Gemalto, which are both along the lines of, we don't think these are relevant to most of our important customers' scenarios and all this sort of stuff. And almost nobody else did anything except ask us who else was vulnerable. So that was the standard response. I think you're doing great work. Who else have you managed to attack? Yeah, so there we go. But there was some more positive reaction, at least from there's a word missing. So Toucan is now being used by Boeing, the aircraft manufacturer, and a major UK-based bank whose name I haven't put on the slides, but you might be able to guess, to analyze their PKCS11 equipment. So in that sense, this might actually help to move the market on a bit and get better responses from the manufacturers. Yeah, so all those results were all for little smart cards and authentication tokens and those kind of things. But with our partners in the banking world, we've been testing Toucan on HSMs. So then it's quite different because HSMs are more sophisticated than these USB devices. Clearly, they have got a little bit more budget for engineering, and they do make more of an effort to make these things secure. And typically, the attribute policy, so the set of rules that governs what things you can set on and off, is much more complicated. And it really tests Toucan's reverse engineering algorithm to try and work out what's going on inside the box. But even so, Toucan has found many attacks on various different manufacturers, but we're not in a position to put up a table with model numbers and all that kind of thing on at the moment. We found there were very diverse implementations of padding checks. So I talked about the problems that you get with the unwrap command. So yeah, in fact, I didn't show the output from Toucan, so let me just do that. Do that. So way up here, when we did the reverse engineering. Right, so we have a step now where we actually test the device to see if there are any padding oracle attacks. So we take the two algorithms, so here we've got RSA and DES, so we wrap a DES key under RSA, and then we work out what error messages we get back from different padding errors, okay? So recall that in PKCS1 version 1.5, the padding format is the first byte should be 0, the second byte should be 2, then you should have at least 8 bytes of non-zero random padding. Then at some point after that, you have the first 0 that marks the beginning of the plain text. Then you get the plain text, and that should be the end. So what we've done here is we've deliberately made some padding errors in the device. So if you unwrap a well-padded key, we get a CKR OK message. If we have a non-zero first byte or a non-2 second byte, we get a data invalid message. But if we have a 0 byte somewhere in the 8-byte padding, we get a different error message. Okay, this is important. We get one saying template inconsistent. And the same if the key is too long, and the same if the key is too small. The only other case where we get the same message as if the padding was invalid is in the case when there's no 0 at all in any of the blocks. So after the 0002, there are no zeros at all. That means the plain text has length 0, or undefined, in fact. And we notice that this device doesn't check the parity of the DES key. So that's pretty much 50-50 whether your device implements that check or not. So that's really bad, right? Because what you really want is to give exactly the same error for anything except a key of exactly the correct length for the command, right? That will give you the best possible resistance against the Bleichenbacher attack. So any kind of variation like this is extremely bad. And so in this particular one, we can, with our best algorithms, we have a median of 11,300 unwraps would give us the value of would give us a 1024-bit plain text, so that would give us the DES unwrapping key, okay? I don't remember whether this device has a Vaudonnet-style oracle for CBC. Yeah, it does have a variant of that, in fact, because, yes, again, because some of the messages are different, but essentially anything that isn't a well-padded CBC pad or a CBC with RC5 padding block gets a different message from OK, and so that allows us to do a variant of Vaudonnet's attack, in fact. Yeah, and so as I said, on these HSMs where they have obviously got quite a big engineering budget, we found that there's all sorts of different variations of what you get back from these padding checks that enables us to identify padding oracle attacks of various different strengths. So we're currently working on Toucan version 2, which will do lots of things like this a bit better. Better reverse engineering algorithm, a better backend that's more customized towards our kind of models, verify some different kinds of configurations and all that kind of stuff. So just to sum up, so I've given you a little demo of Toucan. I hope I've convinced you that it's a relatively effective tool. The state of the art of security tokens is not awesome. So 10 out of the 18 we tested were vulnerable, and the rest have quite limited functionality. And the recent testing on HSMs has shown that the results there are quite interesting as well. So, well, what can we conclude? Well, clearly PKCS11 is a difficult standard to use, right? I think nobody would disagree with that. So why is that the case? So it used to be that every year at the RSA conference there was a meeting of the committee who edit PKCS11. And for a while you were able to get the minutes of this meeting on the web in some forum somewhere. Now you don't get them anymore, but you can read back over the previous years. And at some point they had a discussion about whether PKCS11 should say things like, don't use that algorithm anymore, that's lousy, or implement the attributes in this particular way. And essentially they ducked out of it. They decided that it wasn't for them, they didn't have the expertise, they didn't really know what to do, and they would rather say nothing than say something and goof it up, right? So they decided just to leave all the algorithms in, leave just the very minimal stuff about the attributes in there, and sort of hope for the best. And yeah, clearly that's not been a very effective solution because loads of products comply to this standard and are extremely vulnerable. And it's not just PKCS11, so I think Christian already mentioned the work by Ross and Mike finding attacks on things like the IBM CCA and so on 10 years ago. And it's not yet clear whether these emerging API standards, so Christian mentioned KMIP and IEEE 1619, will actually be successful. Yeah, for various reasons, right? Because it seems like there's not going to be a lot of uptake for the clever parts of the solution. People just want something that kind of works. So that's sort of a bit of a tough situation. But yeah, so maybe if we can get the results of Toucan sort of spreading around a bit more widely, then that'll sort of push people into getting involved with getting better standards together, and this will try and fix one bit of cryptographic practice. Yeah, and just to finish, to give you a couple of URLs, so you can find some stuff in a demo video of Toucan at the project website. And if you're interested in the subject of security APIs, Mike Bond and I co-organize an annual meeting looking at analysis of security APIs, and there's a homepage for that on my homepage, which will show you details of the previous meetings and the next one and all that kind of stuff. Okay, thank you.
Any questions? So I'll ask one.
Somewhat silly question.
Oh, sorry, go for it.
Do you think it's better to have devices with limited functionalities rather than rich functionality and just get around the whole problem? 'Cause I mean,
well, if what you want to do with a device only requires you to sign stuff with a private bid and give the public bid out, then yeah, buy a device that only does that. That makes total sense. Yeah. But the problem is that, especially in things like the banking world, they really do want to share symmetric keys between devices, right? To have many HSMs that have a key available to verify pins. They don't want to have just the key in one place and this kind of stuff. So there are real use cases where you need this more advanced functionality.
To what extent are these devices configurable through a management interface? So I understand you can actually turn a lot of these features off if you want.
Right. So for these little authentication tokens, it's quite rare that you get to change anything. For the HSMs, yeah, absolutely. So there's usually a different way of logging in and then some extra passwords and so on, and then you can turn on and off certain things. And so, yeah, so the fun thing to do with Toucan is to try turning those things on and off, then rerun it and see what difference those things actually make. Because typically they don't tell you, right? They don't tell you in the manual, if you turn this off, the effect will be you can't change that attribute or that attribute. It's all very vague. It's something like, you know, insecure keys will no longer be used for unwrap or something like that. And you're like, well, what do you mean insecure key? And so this way you can actually turn it off and then rerun Toucan and see if you can find.
Can you turn off and then on?
Can you turn them off and then on again? Yeah, I mean, if you have access to the configuration mode, then yeah, what you should first do is turn everything on, right, and then try and make
it
an
turn
attack.
off. Maybe they will not set some bits, and when you turn them on, you know.
Yeah, so we have looked at devices that have some physical trip on them that, yeah, so the configuration can only get more narrow, right? So once you've set something, you said you can't do this anymore, you can't go back to the top level configuration mode without wiping everything on the device. Yeah, which is kind of smart for some use cases, yeah.
Chris, right in the back corner.
Yeah. It occurred to me that we have some better APIs, but nobody's using them. And everybody's using this shall we say, suboptimal API. You mentioned at the beginning of your talk that your motivation was to come up with a set of commands which were secure. Would it be possible to design, or shouldn't somebody design, a PKCS 11 conformant device, which ideally is provably secure in some way, and yet does some useful stuff?
Yes. I mean, at this meeting last year, at the API analysis meeting last year, that was one of the things that a couple of people presented, right? So using the features that came into PKCS 11 version 2.2, it is possible to make a reasonable configuration that can do some stuff. But there are some fundamental limitations. One of them is the fact that there's no authenticated encryption mode for symmetric key. Unless you've got that, you're really limited about what you can do. So Christian talked about how important it is when you wrap a key, to wrap along with the key some nice metadata saying, by the way, this is a key that should be used for this and that and not for anything else. And without an authenticated encryption mode, you're a bit stuck. So yeah, so there are some things that really need to be added to the standard, but there is a lot that we can actually already do, and we can do better with.
So the impression I'm getting is that most of the analysis has been based on model checkers. Have people tried to throw theorem provers at it? I mean, it seems that would be the way to try and generate proofs, right?
Right, so yeah, indeed. So there's a researcher at Oldenburg called Sibylle Fröschle, you might have come across, I don't know. Anyway, so she presented at this API analysis workshop last year a proof of a configuration that's secure using some of these fancy features, and that was like a handwritten old style formal methods proof with defining a logic and showing of the proof and all this kind of stuff. But automated theorem proving, yeah, I don't know. So a long time ago, just after this Anderson-Bond paper, there were these guys who used Koch, the Koch theorem prover, to do an interactive proof of the fix that's proposed in that paper for the CCA API. But that's the last known, for me, use of a theorem prover to try and prove this secure.
Christopher, you have a question?
Just a question on the model checking. You said that you have some configurations which should be secure, but you don't find an error in them. Is it because your model checking is not strong enough, or because there's a subtle error? What's your feeling on these configurations?
So there are cases where you use the global state of the device to enforce mutually exclusive paths in the attribute state. So I generate a key like this, and then you can either make it into that kind of key, or you can make it into that kind of key. And then the abstraction that we use, the abstraction is too coarse, and we find a false attack where you can make a key do both of those things. So better abstractions for state is what we would need in our model checker to be able to verify those kind of configurations.
Is the set of things you can do suitable for theorem provers? Because are all the constructions computationally sound?
Yeah, right, okay. Yeah, so you could make a proof in the symbolic model, and then you'd still have this problem of computational soundness, right? So to actually say that this could give you a real provable scheme in the standard model. Yeah, that's also more difficult. So there's another limitation there.
They can have also, one presumes you could do circular stuff.
You get this big problem that you want to encrypt a key that may later be used for encryption, right? And then as soon as you've done that, as soon as it's available for encryption, you can just encrypt the wrap that you had. And now you've got a cycle, and so you have to treat that somehow. And so, yeah. There are problems at that level of detail that we don't have solutions for either, yeah. But that's sort of, we'd still first like to have some symbolic secure things, and then we might try and fix that sort of level of problem.
And maybe you already spoke to this a little bit, but how much work will it be to take the type of tools and go look at for logical vulnerabilities in other APIs?
Oh, right, yeah, so that's
out,
another
check
project.
out.
Yeah. We've got a whole queue of stuff that we want to throw it at as well, yeah. So, and in fact, yeah, so when I talk about Toucan version 2, so the idea is to sort of make everything in it much more generic so that you could give the specification of the API and then say, okay, now you go ahead and query this and fill in the gaps, and then we throw it to the model checker. The model that goes to the model checker is quite generic, right? So then...
So it's just a matter of how you specify the API.
Yeah, exactly. A bit of time with the manual, trying on a few devices, and it should just, in theory, just be engineering.
I'll ask one more question. Your attacks seem to divide into two types, what you might call logical attacks. Unwrap this, wrap that, do this, and then out it pops. And cryptographic attacks, like padding Oracle and Bicode. Has your tool found any attacks that somehow mix and match from these different attack types?
No, that's true. So I guess you could look at the padding and say, well, that could give us that key, and then from that key we might be able to get these other keys, yeah. No, we're not trying to do that. That would be quite interesting.
All unexplored.
Yeah. I don't know. So if you're only if you just want to find a few attacks, you can always just say, okay, let's just look in a shallow space and see if we find something interesting. But But once you have those kind of problems, you're not going to get any proofs of security. So
maybe I could just add that some attacks I've been looking at, you start off with an obvious oracle like that, and then you eliminate the oracle, and then you discover a pure logical attack to move the sensitive data to a different oracle. So I sense a hint of that in pin processing APIs, where if you're not careful about eliminating all instances of the oracle, then a formal tool can be useful to enable you to see which oracle instances are dangerous. So I think there is some potential for a mixed attack like that in the future. But only once the first oracle is fixed.
So have you talked to the manufacturers about padding Oracle attacks too? Or was that wasn't quite clear? Okay, and what's their easy fixes for these things, right?
Right, so for some of them there really are dead easy fixes. So if you insist on using PKCS1 version 1.5, you can lock it right down and say, okay, I'm going to give the same error unless I get a key of exactly the right length with the 0 in the right place for that key. And everything else gets a different error. And then the attack goes back to needing something like 13 million unwraps, which you might decide is okay. For the CBC one, yeah, so the way that it gets fixed usually is you just accept anything. You just say, I'm expecting to get an AES key, so I'll just accept the first 128
I guess,
bytes.
yeah, this is all very unsatisfactory. So are they going to actually talk about implementing
authenticated encryption? So so for example, the SafeNet guys, what they said was like, we're waiting for that to come into the standard, and as soon as it comes in, we're going to put it in. But until we put it in the standard, it's yeah.
But the standard is kind of stuck in limbo.
There is this 2.3 that's supposed to be in public consultation, but it's hard to find out what's going on. I've sent a lot of email to people, RSA and people that have been on the committee, and I've had.
But I mean, the RSA labs are kind of now part of the MC. They only care about data storage in the cloud anyway.
Yeah, well, okay, yeah, I couldn't possibly comment, but yeah, I haven't had any useful email back from them, so let's put it that way.
Okay, so the time is rapidly approaching when the alcohol will be. I can sense the thirst in the air, so I think perhaps we should stop there with questions and thank Graham for a great talk.